A Brief History of Time by Stephen Hawking, read by Mr. Narrator. Chapter 1, Part 4. Hubble's observation suggested that there was a time called the Big Bang when the universe was infinitely small and infinitely dense. Under such conditions, all the laws of science and therefore all ability to predict future would break down. If there were events earlier than this time, then they could not affect what happens in the present time. Their existence can be ignored because it would have no observational consequences. One may say that time had a beginning at the Big Bang in the sense that earlier times simply would not considered previously. In an unchanging universe, a beginning in time is something that has to be imposed by some being outside the universe. There is no physical necessity for a beginning. One can imagine that God created the universe at literally any time in the past. On the other hand, if the universe is expanding, there may be physical reasons why there had to be the beginning. One could still imagine that God created the universe at the instant of the Big Bang or even afterwards in just such a way as to make it look as though there had been a Big Bang, but it would be meaningless to suppose that it was created before Big Bang. An expanding universe does not preclude the creator, but it does place limits on when might have carried out his job. In order to talk about the nature of the universe and to discuss questions such as whether it had a beginning or an end, you have to be clear about what a scientific theory is. I shall take the simple-minded view that a theory is just a model of our universe or a restricted part of it, and a set of the rules that relate quantities in the model to observations that we make. It exists only in our minds that does not have any other reality, whatever that might mean. A theory is good theory if it satisfies two requirements. It must accurately describe a large class of observations on the basis of the model that contains only a few arbitrary elements, and it must make definite everything was made out of elements, and it must predict about the results of the future observations. For example, Aristotle believed Empedocles' theory that everything was made out of elements earth, air, fire, and water. This was simple enough but did not make which bodies attract each other with a force and was proportional to a quantity called the mass and inversely proportional to the square of the distance between them. Yet it predicts the motion of the sun, the moon, and the planets to high degrees of accuracy due to Newton's law of gravity. Any physical theory is always provisional, in the sense that it has only hypotheses. You can never prove it. No matter how many times the result of experiments agree with some theory, you can never be sure that the next time results will not contradict the theory. On the other hand, you can disprove a theory by finding even a single observation that disagrees with the predictions of the theory. As a philosopher of science, Karl Popper has emphasized a good theory is characterized by fact that it makes a number of predictions and could, in principle, be disproved or falsified by observation. Each time new experiments are observed to agree with the predictions, the theory survives and our confidence in it is increased. But if ever a new observation is found to disagree, we have to abandon or modify the theory. At least that is what is supposed to happen, but you can always question the competence of the person who carried out the observations. In practice, what often happens is that a new theory is devised that is really an extension of the previous theory. For example, very accurate observations of the planet Mercury revealed a small difference between its motion and the predictions of Newton's theory of gravity. Einstein's general theory of relativity predicted a slightly different motion from Newton's theory. In fact, Einstein's prediction matched what was seen while Newton's did not, was one of the crucial informations of the new theory. However, we still use Newton's theory for all practical purposes because the difference between the prediction and those of general relativity is very much small in the situations that we normally deal with. Newton's theory also has the great advantage that it's much simpler to work than with Einstein's. The eventual goal of science is to provide a single theory that describes the whole universe. However, the approach to most scientists actually follow to separate the problem into two parts. First, there are the laws that tell us how the universe changes with time. If we know what the universe is like at any one time, these physical laws tell us how it will look at any later time. Second, there is the question of the initial state of the universe. Some people feel that science should be concerned with only the first part. They regard the questions of the started the universe of at any he wanted. That may be so, but in the case he also could have made it develop a completely arbitrary way. Yet it appears that God chose to make it evolve in a very regular way. According to certain laws, it therefore seems equally reasonable to suppose that there are also laws governing the initial state.